Hello all, welcome to the seventh lecture of Congruences. In this lecture, we mainly discuss the section 4.2 that is about linear congruences. The previous knowledge required for studying the linear congruences are mainly the congruences and its properties and linear Diophantine equations. So the linear Diophantine equations is a new concept for us. So first of all, we will see what is linear Diophantine equations. An equation of the form ax plus by equal to c that has integer solutions. That means an equations having integer solutions. If the equations are in linear form, it is called linear Diophantine equations. This was first formulated by Diophantus, hence the name Diophantine equations. So if it contains two unknown variables x and y, then the equation can be written in the form ax plus by equal to c. If there are more than two unknowns, if three unknowns are there, then we will write the equation in the linear form as ax plus by plus cz equal to d, like that. So if the variables x and y, have integer solutions, then this equation is said to be Diophantine or linear Diophantine equations. For example, consider the equation 3x plus 6y equal to 18. We can verify that when x is equal to 4 and y equal to 1, the left side of the equation x is equal to 4 and y is equal to 1. So this is 12 plus 6, which is equal to 8 equal to RHS. So x equal to 4 and y equal to 1 is a set of solutions of 1. So here we are checking whether this has a integer solution or not. So this set equation has a set of integer solution. So this is a Diophantine equation, or more than it is linear Diophantine equation. Now is the equation has this solution only? No. If we consider x equal to 10 and y equal to minus 2, so this will be 3 into 10, that is 30, minus 12. 30 minus 12, which is also equal to 18. That therefore x equal to 10 and y equal to minus 2 is also a solution. That means 3x plus 6y equal to 18 is a linear Diophantine equation. Now find the solutions if any of the equation 2x plus 8y equal to 13. So first of all, we have to check whether this is a Diophantine equation or not. Suppose if there are integer solution x and y, that means there exists some values x, integers x and y, such that 2x plus 8y equal to 13. Then since x and y are integers, we have 2x plus 8y is an even integer. So the left hand side will be an even integer which is equal to 13. But 13 in the right hand side, it is not an even number, it is an odd integer. So this will contradict. That means this equation has no integer solution. So integer solution does not exist for this equation. So this is not a Diophantine equation. Now there is a theorem which gives a number of or when the linear Diophantine equation is solvable, or how many solutions it has, or what is the form of the solution, like that. So let linear Diophantine equation ax plus by in two variables. Linear Diophantine equation in two variables, that is ax plus by equal to c, has a solution if and only if d divides c, where c is a constant in the right, the integer in the right hand side, and d is the GCD of a and b. That means the integers multiplied with a variable x and y, or coefficients of x and y. So if GCD of AB equal to D and if D divides C, then this equation has integer solutions. And If x naught y naught is any particular solution, then all other solutions are given by x is equal to x naught plus b by d into t and y equal to y naught minus a by d into t, where t is any arbitrary integer. So this about the linear Diophantine equation and its solutions. So if the linear Diophantine equation is solvable if and only if D divides C, and if x naught and y naught are any particular solution, then other solutions are given by x equal to x naught plus b by d into t, y equal to y naught minus a by d into t, where t belongs to z. Now we are going to define the linear congruences. In the last lecture and in the previous lectures, we have discussed about the congruences and its related properties. Now we are moving to define the congruences of in congruences involving variables. So if the linear equation is in the form, or if the congruence is in the form Ax congruent to B modulo M, then such a congruence is called a linear congruence. A solution of a linear congruence means it is an integer satisfying this integer x naught for which Ax naught is congruent to B modulo M. So consider for example, we know that 3 into 3, that is 9, is congruent to 4 modulo 5, since 9 minus 4 equal to 5 is a multiple of 5. So 3 into 3 is congruent to 4 modulo 5. So 3 is a solution of the linear congruence 3x congruent to 4 modulo 5. So for x equal to 3, we have 3 into 3, that is 9, and it is congruent to 4 modulo 5. So this is true. That means 3x congruent to 4 modulo 5 has 3 as a solution. But the congruence, now we consider the congruence 4x congruent to 1 modulo 2. We can see that this congruent has no solution, because that is 2 does not divide 4x minus 1, because since 4x is 4 into x, it is even minus 1 is odd, and 2 is an even number which cannot divide an odd number. So 4x congruent to 1 modulo 2 has no integer solution for any value of x. This is not solvable. This linear congruence is not solvable, or this has no solution. Now we are going to find the relation between linear congruences and linear Diophantine equations. We have already told that the Diophantine equations are equations, linear equations which has integer solutions. First of all, we consider the linear congruence Ax congruent to B modulo M. Then by the definition of linear congruence, this means that M divides Ax minus B. Or we can write Ax is equal to B plus M into Y for some integer Y. Or we can write it as Ax minus My equal to B. So Ax minus My equal to B. So if the congruence is solvable, so from this it is clear that if the congruence is solvable, then we have integer values for x and also for y should exist. That means the linear Diophantine equation is solvable, or vice versa. If the linear Ax minus My equal to B is solvable, there are values for x and y, and hence Ax is congruent to B modulo M has a solution. That means these two equations, the congruence and the linear Diophantine equations are congruent, equivalent. So in order to solve the linear congruence, it is enough to solve the linear Diophantine equation, and we have one theorem about the solvability and about the solution of Diophantine equation, and using that we can define the, or we can find the solvability of the linear congruence. Now there is one note. We say that two solutions x and y or x1 and x2 of the linear congruence are said to be equal irrespective of the distinct values. Suppose okay, two solutions x1 and x2 of the linear congruence ax congruent to b modulo m are said to be equal if they are congruent modulo m. അതായത് രണ്ട് ഡിഫറെൻറ്റ് ഇൻഡിജേഴ്സ് തന്നെ നമുക്ക് എന്ത് പറയാൻ പറ്റും, ദേ ആർ കോൺഗ്രുവൻ്റ് എന്ന് പറയാം. ദെൻ ഇഫ് ദേ ആർ കോൺഗ്രുവൻ്റ് വി ആർ ടേക്കിംഗ് ദം ആസ് ഈക്വൽ സൊല്യൂഷൻസ് ഓർ ദ സെയിം സൊല്യൂഷൻ ഫോർ ദി ലീനിയർ കോൺഗ്രുവൻസ്. So all the congruent integers are considered as a single solution or equal solution. So we have to so if both of them belong to the same residue class, if both the integers x1 and x2 belong to the same residue class, we consider them as a same solution or the unique solution x1 or x2, equal solutions irrespective of their distinct values. For example, we consider the linear congruence 3x congruent to 9 modulo 12. It can be easily seen that when x equal to 3, we have 3 into 3 congruent, that is 9. 9 minus 9, that is 0. It is divisible by 12. So, we have one solution 3 for the linear congruence 3x congruent to 9 modulo 12. And whenever we take x as minus 9, then we have 3 into minus 9, that is minus 27. Then minus 27 minus 9, that is minus 36, which is also a multiple of 12. So this congruence also holds. That is 3 into minus 9 is congruent to 9 modulo 12. So x equal to minus 9 is also a solution for the linear congruence 3x congruent to 9 modulo 12. So we have two solutions. We obtain two solutions 3 and minus 9 for this congruence. But we can see that 3 is congruent to minus 9 modulo 12. Because 3 minus 9, 12 divides 3 minus 9, that is 12. 12 divides 12, so 3 is congruent to minus 9 modulo 12. So for the linear congruence 3x congruent to 9 modulo 12, we consider 3 and minus 9 as the same solution. Even though 3 not equal to minus 9, two values are different, but they are congruent under modulo 12. So we consider them as congruent solutions or the same solutions or equal, or consider them as a equal solution. So when we consider, this is not for this only for 3 and minus 1. When we consider the least residue class modulo 12 of 3, residue class modulo 12 of 3, that is the residue class of 3. That is 3 contains 3, 15, 27, minus 9, minus 21, etc. So this set for each value of or each element of the set is a solution of the linear congruence, and all these are equivalent solutions or equal solutions. And hence in this way, when we consider we got a one solution, then all the elements in the residue classes are also solution. So if a linear congruence is solvable, then it has infinitely many solutions. Infinitely many solutions possible. But we are interested in finding the incongruent, non-equal, not equal, that means incongruent solutions. Hence, and obviously these incongruent solutions will lie in the different congruent classes. Hence, if the congruence is solvable, it has infinitely many solutions, but we have to check for the number of incongruent solutions. So, this will be discussed, or we will obtain the necessary and sufficient conditions for a linear congruence to be solvable and in the following theorem. And this theorem, the following theorem also gives the number of incongruent solutions and formula for finding the incongruent solutions. So this is a very important theorem for the solvability of linear congruences. The statement is the linear congruence Ax congruent to B modulo M is solvable if and only if D divides B, where D is equal to GCD of A comma M. So the linear congruence Ax congruent to B modulo M is solvable if and only if D divides GCD of GCD of A comma M divides B. And there has if D divides B, then it has D incongruent solutions. So if D divides B, then it has D incongruent solutions. So the number of incongruent solutions is equal to GCD of A comma M, that is D. In the previous note, we have already seen that the linear congruence Ax equal to B modulo M is equivalent to the linear Diophantine equation Ax minus My equal to B, isn't it? Ax minus My equal to B. Yeah, Ax minus My equal to B. So the linear, if therefore the linear congruence is solvable if and only if the Diophantine equation is solvable, and the Diophantine equation Ax minus My equal to B is solvable. Ax minus My equal to B is solvable if and only if D divides B. Thus Ax congruent to B modulo M is solvable if and only if D divides B. So first part is over. Now we need to show that the number of incongruent solution is actually D. If D divides, when D divides B, we have already seen that D divides B, the LD linear Diophantine equation has infinitely many solutions given by x is equal to x naught plus m by d into t and y equal to y naught minus a by d, that is y naught plus a by d into t. So the congruence has infinitely many solutions, x equal to x naught plus m by d into t, where x naught is a particular solution. So the congruence or the solutions are of the form x naught plus m by d into t, where x naught is a particular solution that is to be determined by trial and error method or any other suitable methods possible. So x equal to any solution of the linear congruence is of the form x equal to x naught plus m by d into t, where t is any arbitrary integer. Now to find the number of incongruent solutions. Suppose x1 and x2 are two congruent solutions of the linear congruence Ax congruent to B modulo M. So since x1 and x2 are two solutions, they must be of the form x naught plus m by d into t for some values. So for some values t1 and t2. So let x1 equal to x naught plus m by d into t1 and x2 equal to x naught plus m by d into t. And suppose they are congruent solutions. Therefore, x1 congruent to x2 modulo m. That is x naught plus m by d into t congruent to x naught plus m by d into t2 modulo m. Since x naught is common in this one, we can cancel it. So we have m by d into t1 congruent to m by d into t2 modulo m. Now by the cancellation property of congruences, we know that d is the GCD of a comma m, and hence m by d is a divisor of m. So m by d divides m. So since m by d divides m, we can cancel this m by d, which is a common factor. And we will obtain by theorem 4.7, we obtain T1 is congruent to T2 modulo M by M by D. That is T1 congruent to T2 modulo T. That means the two solutions are congruent if and only if T1 is congruent to T2 modulo D, or if and only if T1 and T2 belong to the same residue class or congruent classes modulo D. Or in other words, we can say that the two solutions are incongruent if and only if T1 and T2 are incongruent modulo D. Or two solutions are incongruent if and only if they belong to distinct congruent classes. They belong to T1 and T2 they belong to distinct congruent classes. But there are exactly D incongruent classes under modulo D. D incongruent classes or the residue classes modulo D are exactly 0, 1, 2, 3, etc. up to D minus 1. That is, D congruent classes are there, incongruent classes are there. Therefore, the linear congruence, when solvable, has exactly D incongruent solutions which are given by x naught plus m by d into t, where t has the values 0, 1, 2, 3, etc. up to d minus 1. So this form is known as the general solution of the linear congruence. So the linear congruence has exactly d incongruent solutions. So when t equal to 0, we get x naught is one of the solution that we know already, and other solutions are in terms of x naught, and for the values t up to t from 1 to d minus 1. That is the d incongruent solutions are x naught plus m by d, x naught plus m by d into 2, that is x naught plus 2 m by d, x naught plus 3 into m by d, comma x naught plus 4 into m by d into etc. comma x naught plus d minus 1 into m by d. So these are the d incongruent solutions for the linear congruence. Now there is an important corollary for this theorem. Corollary. The linear congruence Ax congruent to B modulo M has a unique solution if and only if GCD of A comma M equal to 1. The proof is very clear, and we leave it for to do as exercise, for you to do as exercise. Just substitute d equal to 1, GCD of A comma M equal to 1. So it has actually the equation of this, so the linear congruence has d incongruent solutions. If d is equal to 1, it has only one solution, that is a unique solution. So the linear congruence has a unique solution if and only if GCD of A comma M equal to 1. Now let's do some examples. Determine if the congruence if the congruences 8x congruent to 10 modulo 6, 2x congruent to 3 modulo 4, and 4x congruent to 7 modulo 5 are solvable. Find the number of incongruent solutions. Find the number of incongruent solutions is solvable. Okay. So first of all, we have to determine the congruence. Determine if the congruences are solvable or not. First, consider this linear congruence 8x congruent to 10 modulo 6. Now here it is of the form ax congruent to b modulo m. So here it is a is 8, b equal to 10 and m equal to 6. D, which is equal to GCD of a comma m, is equal to GCD of 8 comma 6, that is equal to 2, and 2 divides 10. So in the linear congruence Ax congruent to b modulo m, GCD of am divides b. So this equation is solvable. Therefore the congruence eight x congruent to 10 modulo 6 is solvable since 2 divides 10 by the above theorem. And it has d incongruent solutions. Therefore it has actually it has 2 incongruent solutions. Two incongruent solutions. Now equation number 2. 2x is congruent to 2x congruent to 3 modulo 4. Here GCD of 2 comma 4 is equal to 2, but 2 does not divide 3. Therefore this is not solvable. So the congruence is not solvable or has no solutions. Now the third one is 4x congruent to 7 modulo 5. 4x congruent to 7 modulo 5. GCD of 4 comma 5, this is equal to 1, and 1 divides all integers, so 1 divides 7, so this is solvable and has unique solution by the above corollary. Has a unique solution where modulo 5. Now we move to the next example. Solve the linear congruence 12x congruent to 48 modulo 18. First of all, we have to check whether this is solvable or not. Here GCD of 12 comma 18. GCD is the greatest common divisor, that is equal to 6, and we know that 48 is 6 into 8, so 6 divides 48. Therefore this congruence is solvable and has 6 incongruent solutions by the above theorem. By the theorem 4.9. So, and the solutions are given by, or the solutions are of the form x equal to x naught plus m by d into t for 0 less than or equal to t less than or equal to uh, less than or equal to 5. Okay. Where x naught is any particular solution. So first of all, we have to find x naught, any one solution, or this is that is x is equal to x naught plus m. M is 18 by d. 18 by d, that is 3, x naught plus 3t, where 0 less than or equal to t less than 6 or e less than or equal to 5. So this is about the solution. First of all, we have to calculate x naught. We have the congruence 12x congruent to 48 modulo 18. So when we take x as 1, what will be that? It will be 36. 12 minus 48 will come. So it is minus 36. Minus 36 is 18 into 2. Okay, it is divisible. So by trial and error method, we can see that x not equal to 1 is a solution for the linear congruence 1. Okay, therefore the other solutions are, the 6 incongruent solutions are, the 6 incongruent solutions are 1 plus 3t, where 0 less than or equal to t less than 6. That is 1, 1 plus 4, 1 comma 1 plus 3 into 1, that is 4. Then plus 3, then it is 7, 10, 13 and 16. So the incongruent solutions are or x is congruent to 1 modulo 18, x congruent to 4 modulo 18, x congruent to 7 modulo 18, x congruent to 10 modulo 18, and x congruent to 13 modulo 18 and x congruent to 16 mod 18 are the 6 solutions. Are the 6 solutions. In another way, we can solve this as 12x is congruent to, our linear congruence is 12x congruent to 48 modulo 18. 12x we can write it as 6 into 2x congruent to 6 into 8 modulo 18. So 6 is a common factor here in the linear congruence, and also GCD of 6 comma 18 is equal to 6. Then by the cancellation property of congruences, we can have 2x is congruent to 8 modulo 18 by d, 18 by 6. That is 2x congruent to 8 modulo 3. Now again 2 is common in this congruence. So 2x is congruent to 2 into 4 modulo 3, and GCD of 2 comma 3 is 1. Therefore, this implies x is congruent to 4 modulo 3. Now 4 modulo 3 is same as 1 modulo 3, since the remainder is 1 when 4 divided by 3. So x is congruent to 1 modulo 3. So all the integers satisfying this congruence will be of the form 1 plus 3t. So x is equal to 1 plus 3t. For proceeding this as above, we will get all the solutions, all the required solutions. Okay. So in this method, we can solve all the similar problems. Okay, let's stop here. Thank you all.